So the first thing we're going to be doing here is basically integration, but it's written in a different format where you have to actually separate the variables, okay? So they have given us y prime, which is the derivative, right? And then they've given us 2x over y, all right? So we have an issue here. We have a derivative on this side, we have an x and y on this side. And so when they want us to solve the differential, they really want us to take the antiderivative. So the first thing we're going to do is we're going to get our y's together. We're going to move this y over here. Because it's being divided, we would multiply. So we can rewrite this to be y times y prime equals 2x. All right? So I want to integrate. That's what I'm going to do here. Y prime is, I can write that as y dy, pretty much. This is dx right here for both sides. So the derivative of y with respect to x is just the derivative of y. So I can just write that dy. And over here I recognize the 2x dx. Here I'm just going to take the antiderivative like I would. The antiderivative of y to the first power, well, what do? I add 1 to the power. So that's going to be y to the second power. And then I divide by that power, 1/2, right? Over here, I add 1 to the power. It's x to the first power, so it becomes x to the second. And I divide by that. Well, 2 divided by 2 leaves it just a 1x, right? And pretty much this is a general. I don't have a definite integration going on here, meaning I don't have a lower and upper bound. So when I consider this, I also have to do that little guy right there, plus c. In standard form, it's, think of it as standard form that we want to get rid of our fractions, and we want to get the x and y to one side. So to get rid of my fraction, I would multiply everything by my denominator. By the way, if it's just a c and it's a generic constant, multiplying by 2 does nothing. It stays a generic constant, by the way. So this would look like this. Y squared equals 2x squared plus just some other c. I just doubled a constant is all I did. It's still a constant. And standard form would get those on both sides, meaning I would subtract that x squared over. So y squared minus 2x squared equals c. That would be my antiderivative. Because I multiplied the whole equation by 2 to get rid of my fraction, but it's a constant. It's some unknown constant. If I double an unknown constant, I still have an unknown constant. Like c just represents any constant that I want to put there. So whether I put 3 there or whether I put 6 there, when I take the derivative, it will still zero out. So it's still a constant. So I don't have to write 2c. Because I'm not talking about a specific constant. Does that make sense? It's not like I'm solving for a specific constant here. So doubling your constant is just yet another constant, which is represented by the c. So this should look vaguely familiar. All right. K times y is a direct proportion, right? A direct variation, if you remember that. Like y equals kx or something, right? Was your direct variation. And so this means it's directly proportional. Anytime you have something equals a constant times another variable, it means they're directly proportional, which is why it says proportional to y. It says in many applications, the rate of change of a variable y is proportional to the value of y. If y is a function on time t, the proportion can be written like this. One of the ones that we're familiar with is exponential growth and decay. Y equals c e to the kt. That looks strangely like my account equals p e to the rt. I mean, if I were just saying, right, I just changed the variables. But that's because it's an exponential growth function is what it is. Continuously compounding is an exponential growth, right? And so this is basically that. I mean, we're just talking about one specifically says principal with a rate and a time. The other one is just my starting value with a rate and a time. K and T is a constant of change. We could call that a rate, and T represents my time. C is the initial value. Just like in PERT, P was my initial principal that I invested. K is the proportionality constant, what I am continually multiplying by. Also in a monetary form, it's my rate. Exponential growth occurs when K is greater than 0. Exponential decay occurs when K is less than 0. That makes sense, okay? So if something is growing, you'll have a positive constant K. If something is shrinking, decaying, you'll have a negative constant. So you can look immediately at an exponential function and see whether or not it's growing or decaying, if it's a growth or decay type model. And usually in the word problem, they'll tell you too, right? It'll say the population increased. That's a growth. So when you solve for your K, if you get a negative number, we probably did something wrong. If it says the word decay, or if it reduces or whatever, reduces exponentially or something, then you know you should probably have a negative K there when you get to that point. All right. So let's look at this. The rate of change of Y is proportional to Y. Rate of change, that's usually dy, right? dy dt with respect to my time. The rate of change is proportional to Y. And then they give me some factors when t equals 0, y equals 2, when t equals 2, y equals 4. What is the value of y when t equals 3? So we are going to start out with saying my rate of change, also known as the derivative or the change of y, is directly proportional to y. So that would look something like some constant times y, direct proportion. We did this in like algebra 2 and pre-calc, direct proportion. All right. That's the first thing they tell me. All right, so I need to develop some type of formula here. Well, I'm going to do exactly what I did on that first problem. I'm going to do my integration. That's what I'm going to do. And so I'm going to integrate this side. I'm going to multiply across. So I'll have integration of y prime y dx equals, or I will say dt, I think is what we're doing. We're doing with respect to time. And then we'll integrate the k that's left over with respect to time. All right. If I am, and that's 1 over, right? 1 over, there we go. If I am integrating these two, integrating y with respect to t, that's just dy. So I can have 1 over y dy equals that k dt. All right. This part, derivative of y with respect to t is just dy. That's what those are. So it's another way to write that. All right. On this side, I have something to the first power in the denominator. What's the antiderivative of 1 over x or 1 over y? Or 1 over anything to the first power? The natural log, right? ln of y. That's what I'm going to get over here, right? Over here, I am going to get a constant. That's a number. What's the antiderivative of a number with respect to some variable? So like if I just had the antiderivative of 3 dx, what would my antiderivative be? 3x. So this is with respect to t. So this is, my constant is k. So this is k times t plus c, right? So far, so good. Yes? Make sense? Right?
We were getting 2 essays.
How do I get rid of a natural log? If I want to get that y by itself, which is what I'm trying to get by itself, I need to do base of e, right? This is where your brain has to think about properties of exponents. So e on this side, e on this side. Okay? So far, so good? Yes?
Yes.
If I add the exponents, what am I doing to the bases? So x to the 2 plus 3, what's another way to write that? Yeah, or that.
Oh, that too.
Is that a way to write that?
Yeah.
You agree?
Yeah.
I mean, that's the property of exponents. So if I can go one way, I can go the other. That's what I'm going to do on this right-hand side. So on the left-hand side, my y is by itself. On the right-hand side, I'm going to rewrite it to e to the kt and e to the c. Okay? Everybody see that? I have a constant, that's 2.17, blah, 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 whatever e is, raised to a constant. Just like I said, if I double a constant and it's a generic constant, I can just list it as a constant. So I am going to actually list this guy as just my constant because that's some constant, right? So I'm going to say, well, that's y, that's the constant e to the kt. And voila, we have our direct proportion. That is our PERT formula that we just created there. Does everybody see that?
Yeah.
Yep, that's where it comes from. All right, so
we won't do this sort of
that's the proof of it. This is the proof of that little guy right there, okay? That's how we get continuously compounding. That's how we get that formula. It's right there. That's how we get it. It's a constant direct variation is what it is, okay? A direct variation. Now, here's the thing. They've actually asked me for a couple things. Now that I have my actual formula, I can plug some things in to figure out what's going on with my constants here, okay? What's going on with it. And so if I have this formula here and they've given me some information, that's going to help me out, right? First of all, I'm always going to use the zero guy to figure out what my constant is, all right? So setting this proof aside, I'm going to use just this piece of it to solve what they've asked me to solve, all right? So I just wanted you to see where it comes from. When you have a constant like this, you can go straight to this little formula right here, straight to it, all right? So we're going to fill in some things. They said when t is 0, y is 2. So I'm going to plug it in. Y is 2, c e to the k times 0, right? Which is the same thing as e to the 0. Anything to the 0 is 1, so my constant is 2. By the way, if they give you an initial time, c always represents your initial, right? So initial time. So I now know my c. So now my formula is a little more specific, right? Y equals 2e to the kt, right? I know that much. They've given me a second one. When t is 2, y is 4. All right, so now I'm going to use this to solve for k, right? So y is 4, 2e to the k times 2. All right, well, I need to solve. So divide by 2. So I have 2 equals e to the, I'm going to write it like that, 2k. How do I get rid of an e? Natural log of both sides. All right. So I get the natural log of 2 equals 2k. How do I solve for k? Divide by 2. So my k here is ln of 2 over 2. I know that's a hideous number. If they ask you to actually solve for k, you see that it's at approximately 3.3466. If you're going straight to something else, you can actually leave that in your calculator for k. But they rounded it, so we're going to round it. 0.3466. So using the two initial ones that they gave me, what that did is that helped me solve for my k, and it helped me, my c and my k, those two things. All right, and so now that I know those two things, I can really answer anything I want to about any other time that they give me, right? Because I now know my actual equation looks like this. Y equals 2e to the 0.3466t. That is my growth function, all right? And I know it's growing because I have a positive k, a positive rate, all right? So this is my actual equation for this guy right here, okay? Now they've asked me a question. Well, what happens when t is 3? Well, now I can answer that for any t. What do? I just plug it in. It's the only variable I'm missing. So plug in a 3, and you're going to get that when t is 3, when you plug it in, it's approximately 5.657. You just plug it in. All right. So the initial ones help you get to finding what it is. And we did this with smaller numbers and not so quite crazy variable rates and all. They're giving us another initial besides just one. Last time we did this, it was just an initial of 1, right? Suppose that 10 grams of plutonium, and they gave me the isotope because there's different types, 239, which is the one that we have up there, was released in Chernobyl nuclear accident. How long will it take for 10 grams to decay to 1 gram? All right. How long will it take? All right. So we start with 10. We're going to use our y equals c e to the k t right there. Okay. Now here's the thing. If they told me I started with 10 grams, I don't have to go through the process of putting a 0 in. That's going to be my C. Okay? So they told me that I started with 10 grams. I can go ahead and assume one thing, that my C is going to be 10 grams. Okay? Here's something else I can do. I can go ahead and plug in 1 half-life for that T. And I know that in 1 half-life, how much will that 10 be? Well, half of 10 is 5, right? So I know in that 1 half-life, my answer here will be 5. And how long it took it to do that? Well, that was up here, if I look at my plutonium, 24,360 years. How does that help me? That's going to help me solve for my K, right? Does everybody understand that? It's going to help me solve for my K. So what do? Well, I'm going to divide it. By the way, that's going to be 1 half. 1 half equals E to the 24,360K. I do the same thing to get rid of my E. Both sides by my natural log there. So ln of 1 half should equal 24,360K. All right. It's, by the way, a huge number. I mean, it's actually a tiny number, so it's going to be scientific notation when you put that in. Because it's going to be such a crazy tiny number, in your calculator, you can leave it as ln of 1 half divided by 24,360 for your K. And they want to know, how long will it take to decay to 1 gram? What am I solving for if it's 1 gram? They're giving me my Y, right? They want me to solve for how long. That's my T. Okay? So if I were writing this equation out, what's my equation look like? I would say my equation looks like this. Y equals my starting point 10, e to the K. Well, the K is this crazy, I'm just going to leave it like this. ln of 1 half over 24,360 times T. Okay? That's what I'm going to do with that. So because I don't want to, it's going to be this times 10 to the negative 5. It's going to be lots of zeros in front of your right after your decimal point. So I'm just going to plug it into the calculator that way. They've told me what we want it to decay to. We want it to decay to 1. That's my Y. 10 e to this crazy guy here, T. All right? So I divide both sides by that 10. 1 over 10. And then I can get rid of it with a natural log, right? Yeah, so 1 over 10 equals e to the crazy guy, T, right? Natural log both sides. Natural log of 1/10 equals equals the natural log of 1 half over 24,360 times T. So in your calculator, you can actually do all of that. It looks gross, but that's why I don't round in the process, because I don't want to write down all the zeros and all that. So in my calculator, I'm actually going to put it all out there. I'm going to say natural log of 0.1, right? You can do that. Divided by, and I'm going to put parentheses here because we want it to force it to do the division first. The natural log of 0.5 divided by 24,360. Right? So how long will it take in Chernobyl for only 10 little grams of plutonium to go down to 1 gram? 80,923 years. Suppose an experimental population of fruit flies. So, suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day of the experiment. Approximately how many flies were in the original population? So, if they're asking for the original, then they are asking me to find C, right? And they actually go on and get the entire thing up here. So here's the deal. They've given me a couple of numbers to go with. The first thing they've told me is after the second day, 100 flies. So I can think of it as 2 for my time, 100 for my Y value, right? And then they've given me after 4 days and 300. Almost like an XY is what you can think of it, even though we're not using those variables. So I am going to start with my Y equals C e to the KT. All right. And I'm going to plug those in. So I'm going to plug in my 100 equals C e to the 2 times K. And then 300 equals C e to the 4 times K. Yes, so far so good. Solving for C, I would actually divide both sides by e to the 2k. All right? So if I divide this by e to the 2k, by the way, when e to the 2k is on bottom, I can say 100 e to the negative 2k equals C, right? Everybody agree with that? And then I could do the same thing over here. 300 times e to the negative 4k equals C. It's like dividing. I mean, I'm dividing by that, so I'm just writing it with a negative exponent. If they both equal C, what can I do with those? Yeah, I can set them equal to each other, right? And then I can solve, hopefully, for my K. So I'm going to do that. So I'm going to say 100 e to the negative 2k equals 300 e to the negative 4k. So far, so good. Now, here's how I would do it. I would actually divide both sides by that 300. Okay. So I have 1/3 e to the negative 2k equals e to the negative 4k. And then I would divide that e to the negative 2k over. Okay. So then I would have 1/3 equals e to the negative 4k over e to the negative 2k. Can I simplify those like bases? Yeah. So I have a negative 4 minus a negative 2, right? So I have 1/3 equals e to the negative 2k. Everybody see what I did there? I just subtracted my exponents. Negative 4k minus a negative 2k is negative 2k. Negative 4 plus 2 basically is what I'm doing, minus a negative. Now, how do I get rid of it? How do I get rid of the e? Yes, so I can say the natural log of 1/3, natural log here. I get natural log of 1/3 equals negative 2k, and then I can divide by negative 2. So the natural log of 1/3 divided by negative 2 equals k. All right. You're going to get approximately 0.5493. By the way, it ends up being a positive number because natural log of 1/3 is a negative number. So you have a negative divided by negative. So it ends up being a positive. It is positive growth here. All right. That helps me find my K. What do I need to find? What do I also need to find? I need to also find my C, right? You can plug this K into either one of these to find your C. It doesn't matter which one. If you were to plug it in here, 100 e to the negative 2 times that K I just solved for, you're going to get C equals approximately 33. 33 fruit flies. By the way, I'm going to round this to the nearest whole number because I'm talking about an actual living being here. Maybe not a human, but we still can't have half a fruit fly flying around, okay? So look at your logic. If you're talking about fruit flies, you're not going to have a decimal. Round it to the nearest whole, okay? But in order to get any of these, you have to solve both of them. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. If the sales follow an exponential pattern of decline, what will they be after another 2 months? All right. In this case, I really have everything except the K that I need here. So 80,000 is where I am now. Again, I'm going to still use y equals c e to the 2k. I mean, not 2k, kt. I don't know why I'm saying 2k. All right, I'm still going to use that idea. But y is where I am now, 80,000. 100,000 is where I started. That's my c. E to the k, and then time is per month. So it says after 4 months. So I'm going to use a 4 for my time there. And we're going to do exactly what we would do to solve for it. Divide both sides by that 100,000. 80,000 divided by 100,000 is just 0.8. Natural log both sides, just like I would. So ln of 0.8 equals 4 times k. And then k is going to equal the natural log of 0.8 divided by 4, which is approximately negative 0.0558. Am I expecting a negative k? Am I expecting a negative k? Dropped. Yeah. So a quick check of, is it logical? Positive and negative is a quick check of, is it logical? Yeah, that's a logical k. So I can just go right back to my original function here. Y equals 100,000 e to the negative 0.0558 times t. Yeah, they want to know after another 2 months, what's my time going to be? Another 2 months. Read your word problems. 6, okay? So this is a key, like when you're doing standardized tests, they will have the answer, well, what would happen if you plugged in a 2 there? That will be one of your multiple choice answers, I promise, on a standardized test. So plug in a 6 for your time. So t equals 6 here. Plug it in. The estimation is it will be about 71,500 units at that point, okay?